Okay, so how are graphs complicated, Patrick?
Just looking at them, it seems like if you had to find a specific point in the graph, because any I guess point in the graph could have as many dependencies. I don't know what they're called, but
connections or edges.
Connections or edges. Yeah, they can point to as many connections or edges as possible. So just while you're traversing, it seems like it would take a really long time potentially to find what you want to find.
Mm-hmm.
But my understanding may be incorrect, because at the bottom of the article it said the lookup time for a lot of things was just O of n maybe.
Well, I mean, it is O of n because basically a worst case is you're going to have to look at every node, right? Yeah, the question is, how do you look at every node? Yeah.
I mean, especially when you have something like Facebook or LinkedIn, when they have to look at millions and millions of nodes to potentially find the one that they want.
How are graphs different from trees?
There's no parent, I guess.
Yes.
For the individual nodes.
Yes, there's no parent, although you can have directed graphs where which is sort of okay. Now I'll turn on the camera. We'll see how this goes.
What's the selection?
What's that?
What's the selection?
The selection?
What are we learning about? I just sat down because I saw everybody sitting there.
Oh, okay, yeah. So everybody else is learning about graphs. I'm not sure what you're going to be learning about. Okay. So, let's see. If I do this, can people see? Okay. I'm not sure whether it's going to show up at all on the. No, it's really not. Okay, hold on. Yeah, actually, this works okay too. Okay. So. All right. So how are graphs different from trees? Yes, trees are hierarchical. There's a parent-child relationship between nodes. Graphs can be directed. So I can say the direction of this graph is it goes from this node to this node, but it's not necessarily hierarchical in that I can have this node point at this node point at this node, and this node point at this node. That's perfectly legit for a graph. What type of data might you represent with sort of this directional type graph?
Relationships.
Relationships, right? If this person, so at Hackbright, I had a student who did a project that was like a bartering system for skills. And she did this graph where person A could offer, I don't know, shoe shining. And person B wanted shoe shining. Right? So there's this, right? But you can also, right, maybe person B offers massage and person A wants massage, right? So there's also another line going the other direction. And yeah, I should use the correct vocabulary. This is an edge. There's another edge going the other direction. Graphs. They're complicated. Graphs do not have to have a direction. They can, but they don't have to. So if we were talking about friends, right, and we say Celeste and Kelsey, if they're friends, they're both friends, right? It's not like Celeste is Kelsey's friend, but Kelsey isn't Celeste's friend. At this point, my fellow teacher at Hackbright would always would always reference this study that showed that like half the people you think are your friend like don't consider you a friend. So yeah, he was a pretty dark person, probably still is. Right. So, but you know, certainly like a Facebook friend graph would not be directed. You can't be Facebook friends with somebody if they're not Facebook friends with you. Whereas trees are always directed. There's always a parent-child relationship, right? There's no peer relationships for trees. Yeah.
So would Twitter be a directed graph then, since you can follow people?
You can
They don't
follow
follow
people.
you.
Yeah, totally. So Celeste follows Kelsey on Twitter, but Kelsey does not follow Celeste. I know.
I don't follow anybody.
Okay. Yeah, so right, so graphs, so there are two differences between graphs and trees. Graphs can be directed but don't need to be, whereas trees are always directed. And graphs can have cycles, whereas trees cannot. Right? You cannot be the parent of your grandparent, right? Unless you do some weird intermarriage step grandparenting, you know, where you marry your great grandparent, you know. But in general, trees, you can't have cycles.
But a tree is a type of graph, right?
A tree is a type of graph. Yes, exactly. And a linked list is a type of tree.
It is.
Yeah.
Yeah, sure. Here's a parent. Here's my child. Here's my child. Here's my child. It's a pretty boring tree, but it's a tree.
Bamboo.
It's bamboo. Yeah, so every linked list is a tree. Every tree is a graph. Therefore,
The graph is a tree.
Every linked list is a graph.
every linked list is a
Every
graph.
link is a graph.
It's all just nodes and connections between nodes.
I saw the term forest to represent, I think, a graph that doesn't have connections, or it's just like a bunch of nodes or something. I can't remember. I've seen the term forest though in reference to graphs.
I don't know that one. I'm not a super expert in graphs. Okay, so graphs are useful in showing connections. Another part of graphs that we haven't discussed yet is that sometimes the edges are weighted. So for example, if you have like Los Angeles and New York and Chicago, it's possible that a flight from LA to New York costs $1,500, from LA to Chicago costs $600, and from Chicago to New York costs $400, right? So the cheapest way to get from this node to this node is not the most direct way. So this comes up in graphs also. And sometimes the edges are not cost, maybe they're the amount of time, or, you know, like, you know, but there's some number, some quantity associated with the edge. Yeah.
Does TCP protocol use a graph? Like, you're curious, like, you know, because how it like dynamically reroutes.
Oh, yeah. No, it totally does. Yeah. There was actually a problem that I was thinking of giving you, or a link that I was thinking of giving you that talked about TCP as a graph. Yeah. Yeah. All right. So let's talk about, or let's remember when we made a tree. What was our strategy for doing a breadth first search? No, we did the depth first search first. What was our strategy for doing a depth first search? Do you remember?
Going all the way down to the last child on the furthest side of the tree, and basically working our way backwards up each branch.
Yeah. And you always go to the very bottom before you go back up. And if there's any more to go down, you keep going down. And what was the code? If I asked you right now, if I told you that if you could write a depth first search of a tree in 15 minutes, I would give you $1 million without Google. How many of you feel like you'd be able to do it?
I'd certainly try.
Yeah, okay. Well, sadly, there's no money on the table, so there goes your motivation. But yeah, so our general, so let's see. So Celeste, tell us how to do it.
It's recursive.
It's recursive. Good.
Wait, do I have to do it on the whiteboard or
No.
can I do it in a
I
text
just want you to give a more detailed strategy than what James gave.
Okay, so we're gonna use a queue.
We're going to use a queue. Everybody give Celeste a hand.
I mean, okay, so we're running a function. We take the node with the root,
Uh-huh.
and then we look for any children and we add them to the queue.
Okay, we add whatever node we're on, we add the children to the queue.
And then we check. I guess you can go either way. You can check the. Okay, and then we pop off one from
Okay.
the queue and add any children of its to the queue. And keep doing that
Okay.
until
Yeah.
we have no children.
Until you have no, but you also, there's a pretty key point that you didn't mention, which you need to check
Check
whether
that
the
out.
node that you're on is the one that you're looking for.
Right.
Yeah. Okay, good. So I'm looking at this node. It's not what I'm looking for, so I add all of these to the queue. Then, I think actually for a depth first search, it's a stack. And so then I pop off the stack, and then I look at this, and I add each of these to the stack. Then I pop off the stack, and I look at this. And, okay, so that's the general idea. And it is recursive. Can somebody tell me why that wouldn't work for a graph?
Because there's no root.
There's no
I can give you a node to start with.
There's no direction necessarily. Like if it's
I can, there is absolutely no direction, but the way the graph is stored, Celeste will have a set associated of her friends. Right. And so we'll just look at the set. There's no direction, but we can get a set of Celeste's friends.
I'm sorry, is the question, are we looking for a particular friend?
We are. We want to know if Celeste is friends with Jonathan, who sadly has no friends. But how do we know? Sorry, Jonathan.
And you're saying the same strategy won't work with the graph.
We can't do the same thing as we did here. And I'm asking why not.
There's not necessarily a depth. There's not like a high.
Go on forever.
Like, because I could be friends with Kelsey and Bonnie. And
That's okay. If you were friends with us, then Celeste would by definition be friends with you. Or I shouldn't say she would be friends with you, but she would be connected to you. She could use me or Kelsey to facilitate an intro.
Well,
Let's try it. Let's try our
you
strategy.
get caught in the loop or something?
Ah, yes, you get caught in the loop. So if we try our strategy of, if I want to know if Celeste is friends with Jonathan, fine. So I'm looking at Celeste. Is Celeste Jonathan? She is not, as far as I know. And then we're going to take, so we're going to add a to visit, list, and it's going to be Bonnie and Brittany and Kelsey. Fine. And let's say we're going to do a depth first search. So we'll start with Kelsey. And then, and I think I'm going to, let's see. I actually want to see, let's see if Celeste is friends with Brittany, because it'll be more interesting that way. So if Celeste is friends with Brittany, so fine. So now I'm going to say, so then Celeste is not Brittany. So we're going to go with Kelsey. Is Kelsey Brittany? No. But Kelsey has some connections, Celeste and Jonathan. Fine. So now we're going to look at Jonathan. Is Jonathan Brittany? No, but Jonathan has some connections, Bonnie and Kelsey. Okay, is Bonnie Brittany? No, but Bonnie has some connections. Oh, sorry, is Kelsey? We're back at Kelsey. Is Kelsey Brittany? No, but Kelsey has some connections. Jonathan and Celeste. Is Celeste Brittany? No, but she's got some connections. Okay, so do you see where we're going here? Like, I'm never gonna stop. You have to keep track of visited nodes. Somebody did the reading. Yes, you have to keep track not only of what you're going to visit, but what you've already visited. What would be a good data structure to keep track of what we already visited? An object?
Set.
A stack? A set?
I like set because everything in set has to be unique.
Set is good because everything in set has to be unique. Set is also good for another reason. Lookup time is constant. Why did you say object? Because lookup time is constant for objects too. Do you know that sets are just objects without values? They're just keys of objects. We don't need values in this case. The value is also the key. And for a set, is that what you're talking about?
Yeah.
Oh, this is the
JavaScript. The keys and the
Oh.
values are the same.
I'm going with my I'm going with my Python implementation details. Okay, so but yes, so fine. Really? So if you did,
Well, yeah. It's just,
Um,
a set in JavaScript, like there's no
Everything's an object.
there's no keys. It's just like the values,
okay.
and every value has to be unique.
Okay. All right. So let's start coding, shall we? All right. So let's see.
So can I ask one quick question about this?
Yeah, of course.
So if we're just looking to find the connections here, and it seems like most graphs are implemented with like an object that's like, this node has this connections, why wouldn't we just check that object instead of traversing?
Because I'm not checking to see whether Celeste shares an edge with Kelsey, Brittany, or Bonnie. I'm looking to see whether Celeste, whether you can get from Celeste to Brittany.
Okay.
right? In this case, it happened to just be a one edge hop. But if instead we had Kelsey was friends with James, who was friends with Mita, and you know, whatever, right? Celeste is connected to Mita, but she's not friends with Mita.
Gotcha.
Yeah, good question. Okay. Okay, so here's my graph node. What does a graph node need? You understand what I mean by graph node?
Like the first node.
What's that? Data. What defines Celeste? Right, so
Yes.
This. Yeah.
oh crap. Guess what it is in Python?
And then edges.
Again, this is that whole mutability thing. So I'm going to say if, oh, for heaven's sake. All right, so if edges, then this dot edges is going to be edges. Otherwise, this dot edges is going to be a new set.
You don't have to put parentheses in front of the edges or parentheses around the first condition.
I don't. It would probably make it easier to read if I did, though. So. Oh,
Just edges.
yeah. So it actually, yeah.
Put this that edges equals on the other side.
Oh, thank you.
So, why are you assigning edges to null? Because that's never going to be used.
Default value, right?
Yeah, but the default value is if edges is in the way you wrote it, it's going to get defined 3 and make a new set for edges.
Right. And so I could put new set here, but then I have that mutability problem where all of my nodes will be sharing the same set.
Mm-hmm. But I'm just wondering, like, why you even need the null here, because it's never going to be evaluated, because you're just going to, if edges doesn't exist, create a new set.
It'll evaluate false.
Yeah. I mean, I think if I don't include it, it's going to be undefined. So I probably, you know, could just leave that. I feel like this is a little bit more explicit. But yeah, it's also probably just because I'm used to Python, and in Python, you can't call functions without the exact number of arguments.
Should that first equals on line 3 be triple equals? Or?
No. So I'm doing a ternary here. So I'm saying this dot edges, if edges is truthy, then assign this dot edges to be edges. If edges is falsy,
Okay. So
oh, Jesus Christ. Okay. No wonder you were all confused. If edges is falsy, then assign it to be a new set. Sorry about that. Thanks for asking all of that.
I'm confused.
Yeah, thanks for going with that. Okay. So we have a graph node. What does a graph need?
Nodes.
How am I going to store my nodes?
You should first start with one node,
Set.
build a new of graph node.
I think I'm going to make a set for my nodes. I think I'm going to store my nodes in a set. In my friend graph here, nobody is the root. Nobody is
has superiority over anybody else, except for Bonnie. Is there anything else that I have to store for my graph?
There is something like size.
Yeah, you could. I mean, if that was important to you to know how big the graph was without having to traverse it.
It seems like most of the data is going to be stored like in the nodes themselves.
In the nodes themselves.
I mean, probably some type of way to traverse.
I'm gonna need some some methods. What's a method that we want?
Be able to add a
Delete.
node or a vertex.
Add node. Crap, how do you do this? All right, so how are we going to add a node? What should this take? And I actually think that I'm just going to screw this, and I'm going to just say whenever I add a node, I'm just going to make a new set for the edges. So now, so what do I do?
Then you also have to like set the edges properly.
What should add edge have to take?
Take notes.
Yeah.
2 nodes. And what do I do? What do I have to do here?
So would you add node B to node A's edges set?
Exactly. So what's the syntax for that?
Node A dot add edge. Add
Right? That's how we add to a set. I'm accessing the set this way. I'm adding node B.
Then you'd have to repeat it for B to node A.
Because this is a non-directed graph.
We'd also have to check and make sure that both of those nodes exist already.
How do you check whether a set has something? Is it set.has?
Mm-hmm.
So how do I access this graph's node set?
This dot nodes.
And if I were really doing this, I'd probably check node A and node B individually, but or I could just add it to the graph. Which do you want?
Keep it like this.
What's that?
You should keep it like this.
Keep it like this. Okay. All right. So, okay. What else do I want to be able to do? So I have add node, add edge. Let's just try that. Let's just make a graph now.
You
So
have the console log on 20.
yes. Okay. So let's make a graph. So and oh, look, and there's one left for me. Okay. Okay, who wants to be friends? Oh, how are we going to do this? Because we didn't actually like store our nodes. Should we return the node? Okay, I'm going to try and do something really cool. Let's see how it goes. It would be even cooler if I could do this part without the mouse, but I haven't memorized that yet. Okay, so. Thank you. Okay. All right. So let's say Jonathan and James are friends. And then let's make a new node who is somebody none of us are friends with. Let's just do Voldemort. Stephen Grau! Yeah, that's right, man. James is friends with Stephen Grider. All right, so that's okay. It's okay. It's not going to work. So let's,
Well, I gotta be friends with
no, you don't. He's not part of our graph. You're protected by the fact that he's not part of our graph. So let's, oh, screw you. Type error, cannot properly
Saying LG was not defined.
Yeah, but it's because LG wasn't defined. Like my errors started here and then it sort of cascaded down because none of the other stuff could work. Do I have to make these non-arrow functions? Crap. Oh, graph has already been declared. All right, let's try again. Okay, now we're good. So those can't be arrow functions. Clearly, I'm still basically a JavaScript novice. Okay. All right, so now let's. Nope, Jonathan is not defined because cannot read property add of not defined. So if we do Celeste is adding a node Celeste. And it's telling us that node A dot edges, no, here, this dot nodes is undefined. Oh, crap. But this,
Oh, because you said constant on this. On my side.
my concentration is not at its best this morning, as you can clearly see. So thank you all for covering for me, basically. Okay. How you doing? Good. Okay. Cool. And if I do LG dot nodes,
Capital LG.
who did that? Okay, good. So now the nodes is a set. No. I don't want to do capital LG all the time. Okay, so fine. And now let's see if we can actually add a node. We can. And LG is a graph, and its nodes is a set containing a graph node. This is going to get ugly real fast, but let's add everybody else. And we'll also create Voldemort because, you know, why not? And now let's add this edge. Say that again?
Added
Or you can copy that function to the REPL.
Oh, thank you. So now James has his edge. Jonathan has his edge. Celeste is still friendless. All right, Jonathan. The fate of your goodness hangs in the balance. Okay. All right, cool. Maybe I can do a print nodes. Let's just if I wanted to print all the nodes, how would I do that? Because if I do this, that's actually not so bad. But what if I just wanted to print all of the node data?
This dot nodes to that. Oh, well, I would do like object dot values parentheses this dot nodes, and then you get an array of all the.
Ah. Can I do this? Can I do this on a set?
Yeah, set might have 4 each.
Yeah, it looks like it does.
Yeah.
Thanks, code. All right.
Console log node dot data.
You guys see that? I'm just iterating through the node set. This is just because this statement evaluated to undefined. That's just a quirk of the REPL.
It's because you're returning like console log, and that would return.
It's because, well, I suppose so, but no, because this function is actually not returning console log. It's not
It is,
returning
because
anything.
The arrow syntax means it's an implicit return.
Right. So this function is returning console log. but
Yeah.
this function is not.
Okay.
All right, so good. We have 3 minutes for a depth first search. How are we going to do it?
So this is the one that won't work properly? That you can-
Right. This is the one where we need to have visited.
Oh.
You do need to start with a node. You need to say which node you want to start with. I want to know, is somebody connected to somebody else?
And do you have to pass in to somebody else? No, B.
You can do, and origin is going to be a node. So origin is going to be a graph node, and destination is going to be data for the destination. That's how it's usually done. Although I suppose you could do graph node also. You could give it a node as well. I could give you, you could do it either way. Okay, it's going to be left as an exercise to the user. The first person to give me a pull request, well, see, but you guys can just copy and paste stuff, but I'll have a prize for the first person who can whiteboard a depth first search for me.
On a graph?
On a graph. So you can't, there's no reference material.
If we're writing this up.
Can you look at this?
Yeah. Like the rest of these.
Like all of this?
Like write this depth first search for this graph node.
Yeah.
blah, blah, blah structure.
Yeah. You don't need to rewrite the rest of it. You just have to write this function. Okay. I said, Muta's like, forget it. I'm out. Okay.
You're gonna be posting this this code here.
Yes.
Okay.
Okay. Thanks for taking a little trip into graphs with me.
Thanks, Mark.
So now graphs are going to be fair game for morning whiteboarding. Just kidding. But I heard you guys did really well with linked lists this morning.